Oh, and by the way, I realize the notes are not up on Blackboard yet. I was having some trouble with the update thing, but this afternoon everything should go up and then it should start updating properly. The notes from last semester are still there if you want to look at them. So who's done math with significant figures before? So everybody? That's okay. But if you haven't, or if it's been a long time, definitely something you want to review because it is something that we will use this semester exclusively. So if you have a number like 12.01, how many significant figures is that? 4. What about 12? Yeah. And 12.0? 3. So one of the rules is zeros after a decimal place count in the significant figures, and now we know what that is because it's a different measurement. And that's why that word significant is there. So all certain digits and one uncertain digit make up the significant figures all together. The uncertain digit is included as significant. All right, so that entirety of that measurement that you write down is considered significant. What about try to keep the same color scheme here. 12,000. How many significant figures there? Close. Just 2. Just 2. Just the 1 and the 2. The numbers, zeros that apply to the magnitude of the number are not considered significant, are not considered part of the measurement. So the 1 and the 2 are significant, the 3 zeros are not, unless there's a decimal place at the end. And for that reason, when we record measurements so that we don't have confusion about that, large numbers, small numbers, we usually do what to make sure that we're reporting the correct significant figures? Make sure it's not confusing. What?
Converting to a different unit.
Well, convert it to a different unit, but more commonly use scientific notation. Scientific notation will make sure that we have the appropriate number of significant figures. Because the other problem with 12,000 is if you just write 12,000, that's 2 significant figures. If you write 12,000 with a little period at the end, you may have seen that kind of a shorthand before, that tells you that all those digits are significant. But there's no way to say that the 12 and the first 2 zeros are significant, but the last 0 is not significant. You know what I'm saying? Like there's no way we can write 12,000 that shows that. So what we do instead is we write it in scientific notation. That way we can write 1.2 times 10 to the 4th and say, that, okay, that's 12,000 where the 1 and the 2 are significant. We could also write 1.20 times 10 to the 4th. And that tells us that there are 3 significant figures. Same number, but 3 significant figures, and then 1.200 or 1.2000, whatever it ends up being. That way we can report that more clearly. And the same thing for really small numbers, we should say. So if you have 0.00012, that again is 2 significant figures, because those zeros in front are just placeholders, not part of the measurement. All that's saying is you're making a really small measurement here. All right. So you got rules for significant figures. Hopefully that was a little refresher. If you haven't done this in a while, just go back and review, and there's plenty of practice in the book in the first chapter. Okay, arithmetic with significant figures. This is important because, as you probably imagine, if you take some measurement in lab and then you want to convert that to moles, let's say, you're going to punch it in your calculator. Not like that. I'm just pretending. So I'm kidding. And you're going to come up with some other crazy number. Like if you divide by 512, your product's going to come out in your calculator with a whole string of decimals. So you have to pick the right number based on the rules for significant figures. So what's the rules for multiplication and division? A result is going to be the same number of significant figures as the factor with the fewest significant figures. So as an example, I have a couple examples set up here. Yeah. Let's say we take 1.052 multiplied by 12.054 by 0.53. So you plug that into the calculator and you get 6.7208 something, something, something. How do we report that number? We look at how many significant figures are in each of these other numbers. So how many in that one? 4. And in this one? 5, and this one, just 2. And so how do we report the final number? 6.7 with these 2 significant figures. So that 2 tells us it's got to be 2. So our correct answer for moving on with our whatever is 6.7. And again, this is an issue of reporting measurements honestly and reporting the uncertainty in those measurements. If you write 6.7208, you're telling me that this measurement is between 6.7207 and 6.7209. If you write 6.7, we're saying this is between 6.6 and 6.8. So that's a huge difference in the kind of uncertainty you're communicating, and that's why it's important to be clear on that. All right, addition and subtraction is a little bit different. Because you're not generating new decimal places when you add or subtract the way that you would with multiplication and division, you don't just cut it off at the number of significant figures total, but rather you keep the most or the fewest decimal places that you need to. So as an example, probably makes more sense if we use an example. So 2.345 plus 0.07 plus 2.9975 is, whoops, not 5.4125. So how do you decide the significant figures there? Well, the fewest significant figures is the 0.07, so that would tell us just 1. But because we're adding, we're not generating or losing decimal places. And so instead of doing it this way, we actually stack these numbers up, lining up the decimal places, and then truncate the answer to the fewest and round the answer to the fewest decimal places. So we would put 2.345, 0.07, and 2.9975. So that's going to be 5.4125. The fewest decimal places is right here because of the 0.07. So that's where we're going to cut off to round it. And so that answer should be reported as 5.41. With me so far? Good? Okay. Rounding. A couple questions that usually come up. When do I round? And how do I round? So first, when to be round. We generally, because our calculators can do it, we want to carry the extra digits through as far as you can before you round. So you don't have to do, you don't round to the proper significant figures after every single step. You can round at the end. And most disciplines, most scientific disciplines use these rules. You may have heard other rules elsewhere. But if the digit is less than 5, the digit stays the same. So 15.22 rounds to 15.2. If it's 5 or greater, then it's increased by 1. So 121.45 rounds to 121.5. Some disciplines have different rules about what to do when it's a 5. Generally, for chemistry and for physics, it's that you'd round up. So, think you can do that? Okay. So let's use these new skills in some dimensional analysis. This is everyone's favorite part of chemistry usually, converting from one unit to another. It's pretty exciting. You get to write down things and do math. It's not really that exciting actually, but it is an important skill. I don't know, there's a bunch of good stories about this, but several years ago there was a Mars probe that crashed, and it was because of a bad conversion from English to metric. Somebody used the wrong units. So these kinds of things do come up a lot. In things like medicine, where you have all kinds of different weird measurements that come from historical things, these kind of issues come up. So we're going to practice this a little bit. I'm going to assume you've done plenty of this before, but questions like this: how many miles would you walk if you had to walk 10.0 kilometers? Now, if you know how many miles are in a kilometer, that's great, and you could use that. If you don't, you could use some other factors. Generally in this class, the rule will be that you need to know your metric prefixes. You need to know how to convert back and forth between different metric units. You don't need to memorize conversions to and from English, between English and metric system. So when you need to convert between things like miles and kilometers or feet and centimeters, whatever, those numbers would be given to you. So let's do this problem as though we didn't know how many miles are in a kilometer, but we did know these following factors. So we know how many kilometers are in, or how many meters in a kilometer, centimeters, and so on. And we're going to use these factors to set up a conversion between kilometers and miles. Have you done this kind of thing before? All right. So see if you can set that up before I do anything. And then we'll look at it together and see how it compares. Everybody got the numbers down that they need? All right, I'm going to turn the screen off so I can write it up there, and then we'll look at it together. Keep working on it if you're still working. All right, so I realize that this is something that everybody learns and learns in different ways. So I'm going to show you kind of how I do this. If it's not how you do it, you don't have to change how you do it. Whatever's successful, if you got a way that works, just stick with that way. But the way I like to do it is to set up the units first in something like this. So if you set up your units first so that units will cancel as you go through the calculation, cancel from top to bottom, then you have a good chance of you have a lower chance of putting the wrong number in the wrong spot. Because that's often people's trouble with this kind of a technique is like, how do I know if the number goes on the bottom or if it goes on the top for any individual part? And the key to that is following the units. So you'll notice what I've done is in each case, I've written the unit I want to get rid of on the bottom and the unit I want to have on the top. So kilometers cancels with kilometers, meters then cancels with meters, centimeters with centimeters, inches with inches, feet with feet, and then I'm left with miles. Now I can fill in the numbers exactly as I see them from the identities given or what I know. So I know that there are 1,000 meters in 1 kilometer, 100 centimeters in a meter, 2.54 centimeters in an inch, 12 inches in 1 foot, and 5,280, whoops, wrong side, 5,280 feet in a mile. So I did actually just catch myself there, and that's a good example of that. That if you have the unit already there, and then you write down there are 5,280 miles in a foot, you realize like, oh wait, no, there's not. That's not right. So then you know to flip it because the unit's already there. But if I didn't have those units already there, I totally would have just written 5,280 feet divided by a mile and not really thought about it that way. So following the units helps you keep things on the same side. If you calculate that all out, you get 6.2137. How should we report that number based on significant figures?
6.21.
Yeah, 6.21. So we're going to take just the three significant figures and round that way because of the 10.0 that we started with. Sound good? Can you do this sort of thing? All right. So you can practice those in your homework. There will be some nice conversion problems for mastering chemistry. I'm sure you're excited to do that this weekend. Sorry, you have to. It's just you got to be able to do that so we can go on and do some better stuff. So let's talk about temperature. Has anybody ever taken temperature before? Measured temperature of things? Okay. So you know there are these three different scales. We will generally use which one in lab, would you say, probably?
Celsius.
Yeah, we'll use the Celsius scale, degrees Celsius in lab. Of course, you're familiar with Fahrenheit from things like temperature outside. And then has anybody ever measured anything in kelvins? Kelvin scale? What's the point of the Kelvin scale? You know?
It starts at absolute zero.
Yeah, it starts at absolute zero, which means there is no negative on the Kelvin scale. That makes it really impractical for everyday measurements because what's 0 degrees C in Kelvin? Yeah, I think it says, right? Yeah, 273.15. So you say like, oh, it's about 298 degrees out today. It's like a nice room temperature, but that's kind of an awkward number. So we don't use that. But Kelvin is very, very important when we get later in the semester and we have to do calculations with temperature. Because a lot of these equations require that there is no negative temperature. Since temperature is a measure of, or proportional to average kinetic energy of molecules, that we need a temperature to account for all this energy calculations. And anyway, we'll get into that when we get into that. But it's important to not have that negative. So we'll use Kelvin for that when we get there. But you do need to be able to calculate and convert between all three scales. And you'll definitely see this on the first quizzes in the first exam. So let's look at those equations. Celsius to Kelvin, super easy. You just add or subtract 273, depending on which way you want to go. If you just keep in your head that Kelvin is always going to be way bigger than Celsius, then you can keep that straight, which one's going to be. It gets a little trickier converting from Fahrenheit to Celsius. Anybody know those conversions offhand? Most people do. Well, good. Now you all will learn something, and you'll all be able to do that. One thing that is really helpful is remembering a few kind of landmarks on each scale. That helps you know that you've got the equations right, because the equations I'll show you are both pretty similar, and it's easy to get them twisted around. So if you can look at your conversion and see if it's reasonable or not, that's going to be really helpful in you getting it right. Boiling point of water in Fahrenheit is 212, and that in Celsius is 100. You know that one? A lot of people know that one. And then freezing point of water in Fahrenheit is 32, and the freezing point of water in Celsius is 0. Another good one to keep in mind is body temperature. I don't have that listed here, but anybody know those? What's body temperature?
98.1 in Fahrenheit. 98 in Celsius.
Yeah, it's about 37 in Celsius. So 98 or 99 in Fahrenheit and 37 in Celsius. So that kind of keeps you along the scale. So if it says, we'll jump down for a second. Okay. If we say normal body temperature is 98.6, what is this temperature expressed in Kelvin? And you come up with, actually, that's not a great example. All right, I don't have a good example here, but I was going to say, like, if you have a problem that says convert 90 degrees Celsius to Fahrenheit, and you do the conversion and you come up with 12 degrees Fahrenheit, that should go in your brain and make your brain go, hey, that's not right. Because you know that 90 Celsius is close to 100, close to the boiling point of water. So it really should be somewhere around 200 or a little less than 200, something like that in Fahrenheit. So if you're getting some really low number, chances are something went wrong in your conversion. So having those kinds of landmarks can help you get that right. So let's look at the equations. I'm not going to go through the whole derivation. Here, we've done it before, which is why I have it in there. It's in the book if you're interested. But the point of it is that you have to do kind of two parts to a conversion between Fahrenheit and Celsius. Because the zeros are in different spots. 0 Celsius is freezing water, 32 Fahrenheit is freezing water. So you have to align those parts by adding and subtracting. And then you have to do a standard unit conversion because the size of a Celsius degree is bigger than the size of a Fahrenheit degree. There's 100 Celsius degrees between the boiling point and the freezing point of water. There are 180-ish, right? 180 Fahrenheit degrees between the boiling point and freezing point of water. So a Fahrenheit degree is smaller. So you have to do a unit conversion for the size of the unit, and then you also have to do an addition or subtraction for the offset. You come up with these equations. Now, a lot of people, myself included, think of them a little bit differently, just because the fraction always feels a little awkward to me. I like to think of this as Tc equals the temperature in Fahrenheit minus 32, and then that answer divided by 1.8. And then temperature in Fahrenheit is going to be 1.8 times the temperature in Celsius, and that number plus 32. 1.8 is easier to deal with for me than 9/5 and 5/9, and then you're just dividing or multiplying. The thing that I see people get wrong most about these conversions is the order of operations. You'll notice to convert to Celsius, you have to subtract 32 from the Fahrenheit first before you divide. And to go the other way, you multiply first and then you add. And if you mix up those steps, it's going to be wrong. So however you want to think about it to remember to yourself, I always remember that 32 Fahrenheit is not 0. I don't know why that works for me, but that's the little phrase I use to say, like, 32 is not 0, so we have to make the Fahrenheit 0 first before we convert it to Celsius. That's how I keep those straight. However, whatever you can come up with to keep those straight with those order of operations, that'll be good. So normal body temperature is 98.6. What's this temperature expressed in Kelvin? And then outer space is about 4 kelvins. What is this temperature expressed in degrees Fahrenheit? See if you can do those conversions. Did you get some temperatures? To convert to Kelvin, we first need to convert to Celsius. And so that comes out to 37.0. And then we add that to 273.15. And get 310.2 when we truncate for significant figures. Is that what you got? Great. So next time the doctor takes your temperature, don't actually say anything in Kelvin. They'll just think you're a dick. But you could if you want, I guess. All right, outer space is about 4 Kelvin. What is this temperature expressed in degrees Fahrenheit? What do we have to do to get to Fahrenheit from Kelvin? Yeah, we're going to go Kelvin to Celsius and then to Fahrenheit in the same way. So 4 Kelvin minus 273 is going to be minus 269. Okay. Notice the change in significant figures here. When we subtract that 273, we now have 3 significant figures because we truncate at the ones place because of the 4. It's not that there's just one significant figure that we carry through, but at that ones place. So then when we take that 269 degrees C into our next calculation, we're going to go minus 269 times 1.8 and then subtract 32. Sorry, add 32. We get 452.47, which rounds to minus 452 degrees Fahrenheit. Is that what you got? All right, great. So we can do some temperature conversions. All right, let's move on. Now we put density in this section because density is kind of thought of as a unit, and we use density in unit conversions much like we use some other things. But what is density? Mass over volume. That's sure. What does that mean then?
That's sort of the amount.
Yeah?
I don't know how to articulate it well.
Okay.
Something.
The amount of something in a something.
Yeah. So
Yeah.
amount of matter in a fixed space.
Yes, exactly. So the amount, how much space does a given amount of matter take up for a given substance, or how much mass does a given volume of something have? So density is, as you said, mass per unit volume, mass divided by volume, or we can say that that is the amount of mass in a given amount of space. So basically, how much space does a certain amount of matter take up? And density can be expressed in all kinds of different units. Any mass divided by any volume, so it can be kilograms per liter, it can be pounds per square or per cubic inch, it can be, I don't know, anything you can think of. Anybody know what the units of density we usually use in the lab are? Yeah, grams per milliliter or grams per cubic centimeter, which is the same thing. One milliliter is 1 cubic centimeter. So that's usually how we'll express density. And what's the density of water? 1, yeah. which we're going to learn on, is it tomorrow or no? It's in next week is our first lab. Actually, it varies a little bit. Density varies with temperature. And so, yes, the density of water is about 1, and that'll usually be okay for calculations. But when we're doing really careful analytical work, like we're going to do in our first lab, we actually need a more precise definition of, or a more precise value. So we go out to about, when you get out to about 4 or 5 decimal places, the density of water varies with temperature. So it's like 0.999 something something, depending on the temperature. We use density in calculations much like any other conversion factor or unit conversion like we just talked about. And so we can calculate the mass in a given volume of something based on its density. So the mass of 10 milliliters of ethylene glycol, we're given a density. If it's 1.1132 grams per centimeter per cubic centimeter, and then we've got 10 milliliters, what's the mass? Can we do this without calculators? Let's see. One cubic centimeter is the same as a milliliter, so we can set that up. And we should, let's just say it's 10.0 so we don't lose all of our significant figures here. So milliliters can cancel just like in any other conversion, and we're left with 11.1 grams. All right. So let's do a tough one. Let's challenge ourselves a little bit. This is a question from the book. Liquid nitrogen has a density of 0.808 grams per milliliter and boils at 77 K. Anybody here ever played with liquid nitrogen? I'm sorry, used liquid nitrogen in a scientific context? Don't play with it. It's kind of dangerous. Has anybody ever have any experience with it? No? Yeah? Some? What did you do with it? Nobody ever did anything fun? You know, like made ice cream with it or anything?
That's the stuff where they froze and broke a rubber ball. And
Yeah, yeah, that kind of stuff. So freezing and break rubber ball. We'll get to use, not play with, but use some liquid nitrogen in here. And maybe we can make some ice cream or something. So, all right, anyway, you buy it in these huge tanks. We've got a tank over in the instrument room, you can see, big 175-liter tank. And the liquid vaporizes to gaseous nitrogen, and gaseous nitrogen has a density of 1.15 grams per liter. So note the unit change. The liquid nitrogen's density was given in grams per milliliter. The gas nitrogen's density was given in grams per liter, because gas is so much less dense that the numbers in grams per milliliter would be really, really small. So let's say all of the liquid nitrogen vaporizes from this 175-liter tank in a room, 10 meters by 10 meters by 2.5 meters, which is like a typical room like this. What is the maximum fraction of the air in the room that could be displaced by the gaseous nitrogen? So this is kind of a safety type question. One of the big dangers of liquid nitrogen, besides the fact that it's really cold and can burn you, is that it expands quickly. Like when you pour liquid nitrogen out, it makes all that smoke and everything. The gas forms so quickly that it can displace the air of whatever container it is, whatever room it is, and you can suffocate because there's no more oxygen in there. So there are rules about, like, you shouldn't transport liquid nitrogen in a car. You shouldn't transport liquid nitrogen in an elevator, because if it were to spill, even if it's not like explosive or anything, if it's well contained, if any of it were to spill or get out, suddenly you could lose all of your air in that container and you could potentially suffocate. So it's important to know how much air a given amount of liquid nitrogen could displace. All right, so this is a big problem because we've got a lot of stuff to do here. We've got to figure out how much liquid nitrogen we have, how many grams of it we have to start with, and then how much space is it going to take up when it converts to a gas, and then how does that compare to the volume of the room? So anybody remember from geometry class, how do you calculate the volume of a room?
Length times width times height.
Yeah, length times width times height. So it's going to be 10 times 10 times 2.5. That's our volume of the room. There's a lot of weird questions like that in this chapter, by the way, where you have to go back and remember your volume of a cylinder or volume of a sphere. So have fun with that. You don't have to know those for the quizzes and exams, but you'll have to look them up for some of the homework problems. So since we got full class here, work in groups of 4 at your tables and see if you can work this out. And because there's a few different parts of it, if you want to kind of split up some of the different calculations you might need to different group members, what I would say is first talk to each other, introduce yourselves, because you probably don't remember each other from yesterday, and then decide how you're going to attack this problem, and then take the pieces, calculate what you need to calculate, and see if you can put it all together. If your whole group has no idea how to start or get stuck in a spot, just flag me down. Yeah. You talking to me?
No.
Okay. Okay. Okay, so that's good. That's a good start. So you can go actually much better. Yep. Yep. So we can do. Yep. And once you have so that would be that. Oh. Okay, so that. Doesn't seem right. Remember that the 175 meters, and the density is in grams. You got it? So, yeah. So where are you at? Alright. Okay. What's your plan?
Well, I would compare it
Yep. Okay. Because you've got 175 meters, right?
Yeah.
Yeah. That would be Yep. So once you put in the grams with the blue button, use that to find the case. Start with that and see how it works out. Good. Ready? So what do you raise that? Oh, yeah, you're not going to check here. That's a little bit. No, that's the 808.
Yes.
So that's going to give you basically. Yeah, the same amount of liters, but it's liquid or gas across the gram side. And figure out how many grams you have in liquid, change it back down, these are something gaseous. Yeah, so it's acid. Divided by,
Yeah. A lot more managed.
That's possible. I don't know the answer, but that's possible. That would mean that, yeah, that it could displace all the air and then some. That's what you get.
Yeah. Well, once you know your gas, once you get has divided by your mass,
Think about a liter stick. You about a half stick.
and then you have to change the.
That'd be a lot bigger than a liter.
Centimeters.
That's that person's right. So that's probably. We're almost out of time, so I want to talk about this briefly. We're going to start with this next time, so we won't get through the whole thing. But I want to give you a general plan, and then I want you to keep working on this as you're going through stuff this weekend. So what you want to do here is realize you've got this big tank, 175 liters, and it's filled with nitrogen in a liquid phase. And so when if that were to all evaporate, you would still have the same amount of nitrogen, but now it's in a gas phase instead of a liquid phase. And that's the idea that it's filling the room. So the plan here is to take your 175 liters of nitrogen and turn it into grams. How many grams is that? And you can do that by using the volume and the density. Volume times density is mass. Now you have to do a little conversion in there because that 0.808 is grams per milliliter and the volume is in liters. So you can convert the liters to milliliters, which is 175,000, and then multiply by the density. Or you can convert the density to grams per liter and then multiply by 175. So that tells you how much nitrogen you have, and that's the same amount as that becomes the gas. So then when you have a certain number of grams, whatever that is, we'll say question mark of grams, we can now divide that by 1.15 grams per liter. Grams will cancel, and we end up with liters of gaseous nitrogen. Liters of nitrogen gas. And that's how much nitrogen gas is filling the room in liters. Now the next part is to compare it with the size of the room. The other tricky part of that is that the room is given in meters. So your volume that you calculate with your length with height is going to be cubic meters. But a cubic meter is not the same as a liter. So you have to convert from cubic liters or cubic meters to liters, which you can look up a conversion factor for that, or you can convert both of those volumes to a different thing. One thing that I would recommend is if you converted these all to centimeters, then your volume would be in cubic centimeters, which we know is like milliliters, and that makes for an easier comparison. So keep thinking about this, keep working on it. We're going to come back and talk about it at the beginning on Tuesday. Lab tomorrow is check-in, and so we will be learning how to be safe and all of that. 9:30 tomorrow, next door, back next door in the other room. Welcome back. Yeah.
I'm curious.
Okay, I know, yeah. It's basically the same. You guys have a Blackboard or anything
Yeah,
like
yeah.
that?
I didn't.
Okay. Yeah, everything should be pretty much the same then. Stuff. What? Yeah, great. So see you live tomorrow.
I wasn't here yesterday, so I
Yeah.
just wanted to know if there was anything that I missed.
Did you get into Blackboard and kind of look through stuff?
Yeah.
Okay, so just look through the syllabus, make sure you got what you need. The Mastering Chemistry's homework you need to get. A textbook is kind of up to you if you want to get like a current version or an old version. What's your name, by the way?
Tiffany.
Okay, I'm Joe, so welcome. I see you're the one who wasn't here yesterday. Other than that, just look through, and make sure that, let me know if you have any questions. We'll start lab tomorrow with check-in and safety stuff, which is next door, like the next room over.
Awesome. Thank you.
All right, yeah. I'll take it. I've got a little pile of them here.
For that website, what's it called again?
Mastering Chemistry.
Yeah. Where do we get the code from? The site or the school library?
The site itself. If you buy a brand new book from the bookstore, it kind of comes as a big package with the code in it, but it's expensive to get that whole big package. So if you just get an old book, you can go directly to the site and say that you want to sign up, and you just sign up for it and with the code that's on Blackboard and pay whatever it is, and then you're in.
Okay, thanks.
And if you need some more time with that, just let me know and we can move the due date back.
On Blackboard, where do we check like what's our home?
What do you mean?
Like I don't know what's due tomorrow, you know.
Oh, well, in general, the only things that'll really be due, lab reports will always be due the next lab period. We'll talk about that tomorrow when we talk about lab stuff. And the Mastering Chemistry has the due dates listed on there, like the online homework.
Okay.
Yeah. Other than that, that's pretty much it. It's just quizzes and exams.
Do we have any homework for like due tomorrow?
No.
Or on Thursday? No.
So earlier you said that the lab we're doing is next Thursday, but we're doing like something else tomorrow. 'Cause